So welcome back. There are certain things we are going to talk about Coulomb's law, that discussion, and will today concentrate on the vector representation and then introduce to you the electric field concept along with what is known as superposition, which we have done. I explained it out to you earlier. So the Coulomb's law, as was proposed by Mr. Coulomb, F is equal to 1 upon 4 pi epsilon naught, Q1, Q2 upon R squared, Q1, Q2 are in coulombs and R is in meters, and this is the constant, the system which depends upon the system itself. All these quantities Q1, Q2, R and F, they are variables, but this is the constant of the system, and which we know that the value is 9 to 10 to the power of 9 Newton meter square per Coulomb square. Okay. Now, let us take these two charges located at the point 1 and point 2 with the name number 1 and number 2. Okay. And they are at a distance r apart, which has been just shown over here as a vector quantity r12, like that. Okay. I don't care right now whether these charges are both positive, both negative, one positive, another negative, like that. Where the force is of attraction or repulsion or whatever, it doesn't matter at all. Okay. So in that general condition, if I have an origin of coordinates O over here and I draw a line joining O with 1, I get R1, vector R, whose magnitude will be equal to R. Okay. Vector R2's magnitude will be equal to R2. Okay. Let me write R1, R2, this is the magnitude of the vector. Okay. And here it will be R12. Doesn't matter. I write it here. Right, sir? Okay. Now, I have spent ample amount of time on vectors and their properties. Right now, what we can say by the head-tail method of vector addition, we can also take the parallelogram law of vector addition, etc. But what we find is that the vector this is the head and this is the tail, and plus vector this is the tail and this is the head, and then the sum of these two vectors, this plus this, will be the resultant vector which we have here, R2. If I write it in mathematical terms, then R1 plus R12 becomes equal to R2, so that I can write R12 vector as R2 minus R1. And similarly, R21 is equal to minus times R12, R1 minus R2. That's no problem. Let me remind you that there is a cap vector, and that cap vector is basically a direction vector, okay, a unit vector, okay, and this is equal to vector R1 divided by the magnitude R1, and here R2 cap is equal to vector R2 divided by R2, okay, and I can write the cap vector, the unit vector in that direction as R12 divided by R12, and here vector R12 divided by R21 divided by R21. Is that right? Nonsense. It's not right. Okay? We cannot divide a vector by a vector. So what we have to do is we have to take off this vector. Why can't we define? Why can't we divide a vector by a vector? Because it's not in the definition of vector algebra. Okay. Division by a vector is certainly haram. It's not allowed. Okay. So now I can write the Coulomb's law in the vector representation as F12 is equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R12 square R12 cap. This means vector R2 minus vector R1. This can also be written as, look here, look here very carefully. I have written 1 upon 4 pi epsilon naught Q1 Q2 upon R12 cube multiplied by vector R12. So this is also one of the methods of writing and confusing you. And when we are testing you, we got to confuse you. Okay. So that, and confusion is a very nice state of mind, because if you are confused, good, very good, you know something. Okay. When you remove the confusion, then you know more. Okay, friends. So similarly, I can write vector F21 is equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R21 square cap vector unit vector R21 cap. Okay. Or like this case, 1 upon 4 pi epsilon naught Q1 Q2 upon R21, okay, whole cube multiplied by vector R21. Okay. So this is the way to express the Coulomb's force. Of course, we'll see that F12 plus F21 will be equal to 0. Okay, and that means it says to Newton's third law, yes sir, yes sir, yes sir, yes sir. Okay, no 3 bags full. Okay, so that is it. It's not very difficult. It's a matter of 5 minutes of concentration. Scribble it twice, thrice by yourself, and you will understand what it means. R21 means R1 minus R2, and R12 means R2 minus R2. Okay. So this is the way that we deal in two vectors. There's the minimum set of vectors. I'm sorry, two charges. This is the minimum set of charges, which gives an idea about what the forces are and what are the directions of the forces. Okay. Now, I told you about superposition. Superposition in the case of waves, and otherwise also it is a kind of a algebraic sum over there. But here in this case, because vector quantities are involved, so we say that this is a vector sum of two things. For example, I am taking Q1, Q2 and capital Q located collinearly on the same line. Okay. Line joining Q1 and Q2, Q1 and Q, Q2 and Q is one and the same line extended. The distance between the two lines I am taking at x, two charges Q1 and Q2, and Q2 and Q I take as x prime. So the distance between Q1 and Q will become equal to x plus x prime, x dash, and between this and this will be like this. How they are set over there, that's our imagination. Wallah alam bisawab, Bhagwan jane. Okay, only God knows. Imagination, the most strongest thing is the imagination that happens. Okay, let it be and be. Tathastu, tathastu. No problem. So in this situation, what I am showing over here, that the force on this, naturally I have shown it like that because both of them were plus. So the force on the charge capital Q due to, I'm sorry, this is because of Q1. So I write it as Q1. F Q Q1. On Q due to Q1. And the second is I have shown here separately, but it's actually on the same line, and this is F capital Q Q2. The charge on capital Q due to Q2. Both of them are on the same line, and therefore it is easy to just calculate them because they are on the same line. So I will say that the net force acting on this capital Q is equal to, I am writing it like this, F on Q due to the two charges Q1 and Q2. This is equal to the sum, this force plus this force which I have represented here. So there is no problem. Okay. Well, sometimes what happens is that I have shown a charge Q naught here. Okay, and I have shown you 4 forces, F1, F2, F3, F4. And I have not shown you what there could be a negative charge in this direction, because if this is positive, if we are taking it as positive, then there could be a negative charge in this direction located somewhere here, or a positive charge located in the opposite direction of what has been shown. One charge or a number of charges. That set of charges gives us a force F1. What is our job right now is that similarly F2, F3, F4. I'm just taking it randomly. This could be due to one set of charges. This could be another set of charges, or a single charge, and set of charges, a single charge, distribution of charges, etc., etc. So what is evident is that we find that there are F1, F2, F3, F4, 4 different vectors are there, and we have to add them algebraically using the concepts of vector addition. Okay, using the concepts of vector addition, and you can take the head-tail method, or you can use the parallelogram law of vector addition, the triangle law of vector addition, or polygon law of vector additions, etc., etc. Okay, you can build up that you can see there. Okay, in the main text of vector algebra that I introduced to you, or you can even probably, if you visit the lecture that I had for the Newton's law of gravitation is still there. There also any set of vectors have to be added according to the vector law of addition, and maybe I get a resultant, okay, anywhere of these forces F1, F2, F3, F4, F5, F6, X7, and so many multiple like that. Normally, what we teachers do is that we give you some geometrical constructs, like a triangle, like a rectangle, like any of that kind of polygons. Okay. Now, for example, this net force could be 0 and could be non-zero. If that net force over there is 0, then we say that this point is a neutral point for the system of charges which give rise to forces like this. Okay. If not, then there is a net value which is there, and we have got to calculate that, we got to do that. Okay. So there are a lot of questions which are posed to you, and you are supposed to do that. The next item which comes to us is the beauty, and this concept which I have already discussed in the case of gravitation. Okay, the field concept. You know, who gave the field concept? He didn't have formal education like what you are having. He was not even high school, and he was one of the greatest scientists, okay, who was working for Davy's lamp, and his name was none other than Michael Faraday. Okay, he gave the concept of field lines, magnetic field lines, electric field lines. Of course, he didn't talk about gravitational field lines, etc., etc. I'll talk to you about this. But electric field or magnetic field or gravitational field or this field and that field, okay, you feel, me feel, they are just concepts which cannot be measured directly. I'll tell you about the field concept. Enjoy that and hope that you also enjoy. But you have to be very careful with me for the next training. Okay? So let me tell you about the electric field concept. The beauty of the electric field. A field concept, as I told you, was given by Michael Faraday, but he was not working on electrostatics. He was rather working on the magnetic concepts, wherein there was a relation between EMF and flux lines, and when he talked about those flux lines, then he said that if there is a space and more lines pass through it, then the strength of that field will be more. Anyway, there will be occasion to talk about Faraday and his beautiful mind that he had without a formal education like you have. Okay. Electric field concept. I make it very simple for you in the first instance, and then talk about things. I have a charge, maybe I call it plus Q. Plus Q. And there is another charge which I call Q naught. The separation between the two charges is R, as has been shown. Let us, and what we see is that on this charge Q naught, which we will call and normally call it as a test charge, okay, there will be a force F. I've shown it in the actual direction because the two charges are plus and the line joining, and then there is a repulsion that will occur, etc. And this is, I can also say that this is the force on the charge Q naught due to the charge Q. Okay. Now let's see as to what will be the magnitude of the force. The magnitude of the force will be equal to 1 upon 4 pi epsilon naught Q naught upon R square. Okay. Q is defined, R is defined. When I say defined, it means it is now, it has been fixed by you. It has been fixed by you. So this I can write as 1 upon 4 pi epsilon naught Q into 1 upon R square Q naught. Or putting them together, first time I am writing it like this, Q upon 4 pi epsilon naught R square multiplied by Q naught. Now what we find that if we make the Q naught variable, still keeping it as positive, a very small, maybe infinitesimally small charge, etc., etc., then I can say that F is proportional to Q naught. It's very simple. A system is there, and if so, then I can write this whole thing as a constant, give it a name, okay, E, okay, a constant E multiplied by Q naught. So this becomes a system of proportionality, and I can write from here the value of this constant E is equal to F upon Q naught. And like all cases that we have discussed so far, y is proportional to x, y is equal to kx. So k is not a function of what? Is not a function of x comma y. Okay? So similarly, I can just write that from here by algebraic manipulation I can write E is equal to F upon Q naught, where E is not a function of either Q naught or F. Okay. Is rather a function of the system, not system, the system, I say, al-nizam, whatever it is. Okay. And if I use the notations associated with the vector algebra, then I have to write on this side, because this is a vector divided by a scalar that will give you another vector. So this side also there should be vector. So we find easily that this quantity E is also a vector. And if Q naught is more than 0, that is positive, which we have taken over here, then of course the unit vector E cap will be parallel to the other unit vector F cap. Okay. Now if I plot this force F as a function of Q naught on the x-axis in coulombs and F in Newton, then I get a straight line. And this straight line has got a slope, and that slope is E. I can write this as delta F upon delta Q naught or dF upon dQ naught. Okay. So this is the interaction of the electric field and its magnitude. Now, I have a point P in space with coordinates x, y, z, anywhere. And we find that the electric field is of this magnitude and in this direction. Okay. Now, what is important is that at this location, the presence of a Q naught is not essential. Okay? It may be present, no. When I say it's not essential, then let's take it away. Q naught. Okay? Mentally, we take it away. So this E is a function of what? The location of the point in space, and also the charge distribution because of which this has come up. I can tell you, this is a concept, a beautiful concept. It is not physical, but it is very effective and helps us understand the electrical systems, the magnetic systems, etc. Easily. So E cannot be determined, cannot be measured directly. How can we measure the value of E over here? By putting a small test charge over there and trying to find out as to what is the force on it. Then divide it by that test charge and we get the value of E. Now, this E could be because of the presence of a single charge, positive or negative. Because of the presence of a very large number of discrete charges or ensemble of charges, assembly of charges. This could be because of charge distributions, linear charge distributions, spatial charge distribution is over a space like this, or surfaces or volume charge distributions. We don't care. Okay? We don't care. Now, our relationship is, of course, you know my name. Today you can see my face, but if I was only talking to you in a voice and I was telling you things in a classroom, okay, do you care who my father was? Do you care who my grandmother was? Do you care who were my neighbors at different? No, you don't. So you don't want to indulge into the history. And similarly, your teacher looks at your faces, okay, but he teaches you because he is competent to teach. And you go to him or her in order to learn because you have the urge to learn and because you want to progress. So similarly in this case, no history is required. No description of why this field is there. But this is enough that the field is there, and the field has a direction and the field has a magnitude. Like all vectors, they have a magnitude, they have a direction, etc. So similarly the field is there. We will talk. I stop it here because it is a very valuable concept. Please go through this lecture twice or thrice, not less than 2 times, even if you are an Allama, okay? If you are a Prakant Pandit, still you have to go twice through and try to understand me, because the things I am talking to you about in a simple fashion, they may not be as simple in the books. They make that complicated and test your brains. I don't. Okay? I believe that you have got the guts to understand these simple things. They are simple. Physics is very simple. Okay? It's based on logic. It answers our questions. So, the electric field, and thereafter I'll continue with that. Maybe I take example of certain numerical examples I'll give to you, and then I talk to you about what are the field lines and how field lines they scatter in, and that is where the concept given by Faraday and later on given by Gauss, that will be of help to us in understanding the concept of field. And once you understand the concept of field, it is very, very essential that you put the concept over here for all times to come. Okay, and then you are a Raja Beta or Raja Beti. Okay, whatever you survey, you are the king of Tartary. Okay, and therefore all you kings and queens of, no queens, female kings and male kings that I have in my company, okay, I bless you, and I hope that you understand these things. Please do go through 2 or 3 times so that other things becomes easier for me to communicate to you. Thank you very much.